Today's video will be on antiderivatives. Basically, we will be going in the reverse of when we take our derivatives. Essentially, think of it as we will know the derivative, and we will have to go backwards to figure out what that original f was. Well, if we have x squared, before that must have been an x cubed. The cubed would have come out front to give us the 3. However, there could have been other stuff afterwards. This could have been x cubed plus 1. That derivative would give us 3x squared. We could have x cubed plus 2. We could, in fact, have x cubed plus or minus any constant afterwards, and it would give us this derivative. So if we say f of x is equal to 3x squared, the notation we see for the antiderivative would be capital F of x. So we're essentially going backwards from 3x squared. We just said that would give us x cubed, and then we represent that it could be any constant with a plus c. That c represents any possible constant, because when we take the derivative, it would just become 0, so we wouldn't see it. The antiderivative is essentially a family of functions, because it's a whole bunch of functions that could just be shifted up or shifted down, and they will all share the same derivative. So lowercase f of x would be the derivative of capital F of x in our notation, meaning if you took the derivative of capital F of x, it should give us lowercase f of x. So we just saw this one. So the x squared, we knew originally that was x cubed, and the 3 had come out front. So 3x squared's antiderivative would be x cubed plus c, because we could have any constant. Well, what about if we had x squared? The thing that came before that, so think of it as before you took the derivative, what did we have to end up with a derivative of x squared? Well, we know we must have had x cubed. Well, if we think about that, when we take the derivative, 3 would come out front, and x cubed's derivative would be 3x squared. Well, that doesn't work. So we need to think about what must we have had out front, so when we multiplied by 3, it would end up just giving us 1 for the 1x squared, and that would have been 1/3. And then we'll have to put the plus c on the end, because we could have had any constant. So you can always check your antiderivative by just taking the derivative. The derivative of 1/3 x cubed, 3 times 1/3 is 1, and we would have then x squared. The constant's derivative would be 0. If we had x to the 5th, originally that must have been up 1, so x to the 6th. We need to think about what number must have been out front, so when we multiplied it by 6, we just got the 1 back. Well, that must have been 1/6. Hopefully you kind of see a little pattern. Oops, we need our plus c on that one, sorry, for our constant. So in general, if we have x to the n, our antiderivative must have been 1 before that, so x to the n plus 1. Well, when we had x cubed, we had 1/3 out front. When we have x to the 6th, we had 1/6 out front. So this will be 1/n plus 1. Because if we took the derivative, n plus 1 times 1/n plus 1 would just be 1. And then n plus 1, when it's dropped down 1, would give us n, making this the derivative of that. So if we have x cubed, we would have x to the 4th with 1/4 out front. Don't forget your plus c. Okay, and I need to throw the plus c up here as well. If x to the 4th is lowercase f of x, capital F of x, we would have x to the 5th with 1/5 out in front, and then plus c, our constant, on the end. Well, what if we had 1/x for lowercase f of x? we need to think about what function's derivative is 1 over x. Well, that comes from natural log. So we'll have natural log of x plus c, but we have one issue. In 1 over x, you can have x values that are positive or negative. In natural log of x, we need those to just be positive. So our antiderivative of 1 over x is natural log of absolute value of x plus c, because we need to make sure those aren't negative inside our natural log. The reason we don't need to worry about 0 is 0 was not in the domain of 1 over x anyway, because it was undefined there. For sine x, we need to think what thing's derivative gives us sine. Well, if we go through our sequence, we have sine x, cos x, negative sine x, negative cos x, and then we're back to the top. So if we have sine x and go backwards 1, that means we were just at negative cos x, and then our plus c on the end. If we're at cos x and go backwards 1, we just go back to sine x, and don't forget your plus c on the end. And remember, the great thing about antiderivatives, if you want to check your answer, just take the derivative. The derivative of sine x is cos x, derivative of c is 0, so yes, we got cos x, that checks out. Well, just like when we took our derivatives, if you had a polynomial, you could just take the derivative of each part. Same thing with an antiderivative. So x cubed, we've already seen actually. So we have x to the 4th with 1/4 out front. Plus we'll have x to the 5th with 1/5 out front. And then we need plus a constant at the end. Check with your derivative. 4 times the 4th is 1. Then we have x cubed. 5 times the 5th is 1. Then x to the 4th. And then derivative of a constant is 0. So this might get a little bit more challenging. If we have 2x cubed, we know we should have x to the 4th. But we need to think about what must have been out front in order to give us a 2. Well, 4 times a half would give us a 2. Where that's really coming from is we already had 2 there, and we know we normally put the 4 underneath. Well, 2 over 4 just gives you a half. So you can write it as 2/4 or a half, whichever you want. We'll have x to the 5th, and we have 1 over 5. We'll have x to the 2nd, and 1 over 2. So one way you can think of it, these 1s, the reason they're there is because we had 1s in our original. So that's why we could have it as 2 over 4. 2 was originally out front, so it's 2 over our exponent that went back up 1. So we're basically undoing the derivatives, and then each time, make sure at the end that you put on your plus c. Okay, one of the most commonly forgotten things in the antiderivative. It's easy to forget, okay, but we need to have it there because we really don't know what that constant is. It could be any constant we're adding or subtracting on the end. Well, we've got 1 over x to the negative 3. When 1 over x, we had the natural log absolute value of x plus c. Well, this is just going to be natural log absolute value of x minus 3 plus c. Because remember, when we did derivatives of natural logs, it was derivative of the inside over the inside. Well, derivative of our inside is just 1 over x minus 3. So that checks out, and the constant's derivative is 0. So this is a bit messy now. Just like when we did derivatives, it was often helpful to rewrite it in an easier form. Same thing with antiderivatives. Let's first think of this as 4 sine x plus 2x to the 5th over x minus x to the 1/2 over x. Well, then this then becomes 4 sine, oops, I forgot my x here, 4 sine x. This will be plus 2x to the 4th minus Well, you have x to the half on top. This is x to the first on bottom. So if we subtract those, we get x to the negative 1/2. So let's do our antiderivative now. Just like when we did derivatives, if you have a constant out front, basically do your antiderivative rule and just multiply the constant back in. So sine's antiderivative is negative cos, multiplied by the 4, and we get negative 4 cos x. Well, our 2x to the 4th, we know we're going to get an x to the 5th. The 5 will have to go underneath, so we'll have 2/5 x to the 5th. And for our x to the negative 1/2, here it might get a little challenging. If we go up 1, we'll have a positive 1/2. I'm going to do this part off to the side. If we have 1 over 1/2, that really just ends up giving us 2. But notice we had a negative out front, so it was really negative 2 x to the 1/2. Again, if you're unsure about that, check it with its derivative. 1/2 times negative 2 is negative 1. And when the exponent goes down 1, we'll have negative 1/2. And then just don't forget your plus c on the end. So it gets a little more challenging, but you're just doing, in this case, negative 1 divided by 1/2. When you divide by 1/2, it's the same as multiplying by 2, so we get negative 2 there. And if you're ever unsure, just take the derivative and check and see if it works. So here's a little chart. This is also in your textbook of a lot of common antiderivatives. So if you have a constant out front, you can just take the antiderivative and multiply the constant back in, like we just saw with that 4 sine x. If you have things being added and subtracted, you can take their antiderivatives separately. The third one there is our basic 1 over n plus 1. They just put it in the denominator rather than 1 over out front. We saw 1 over x was natural log absolute value of x. E to the x's derivative is itself, so therefore its antiderivative is itself. Cos's antiderivative is sine. Sine's antiderivative is negative cos. We saw earlier this year that tan's derivative is secant squared, so it works the other way as well. And the same for our other three. For secant, we saw our inverse sine and inverse tan derivatives. Well, if we have those things on the left, their antiderivatives would be the corresponding ones on the right. So now we have a constant. We need to think, what must we have had when we took the derivative? It gave us 1. Well, if you're getting a derivative that's a constant, the thing that you took the derivative of must be linear. So we need something that's linear with 1. That would just be x. So we will have x plus c. Now, just one thing to mention here, these are just the rules. Keep in mind you would have plus c on the end of all of them. Okay, that's just assume that it's there. They just didn't write the plus c on all of them. I just wanted to point that out. So here we have a constant of negative 3/2. So our derivative would be negative 3/2 x, something linear, and then plus c. Because if we took the derivative of negative 3/2 x would be negative 3/2. Derivative of a constant is 0. And here's our general form. If we have some constant k, its antiderivative would be kx and then plus c. So here's just another way to notate it also. We saw dy dx could mean the derivative. Well, going backwards to just get y would then be the antiderivative kx plus c. So if we have plain old x and want to do the antiderivative, we would have x to the second, and out front we would have 1 over 2. So again, in general, if we have x to the n, we would have x to the n plus 1, out front 1 over n plus 1. And the reason there's 1 there is because 1 was in front of our term originally. If we have something else, that will just be on top. And we see that in this bottom one here. 3x to the 4th will go up to x to the 5th, and the 3 will now be over 5. Okay, so if it's not 1 there, that just goes in the numerator. That's all. So in general, if you have a constant k out in front, you'll have x to the n plus 1, k over n plus 1, and then your plus c. And it looks like I need to add my plus c's on each of these. And again, what the plus c now represents, because that can be a lot of different things, this is a family of functions. Okay, it's a lot of different possibilities that it could be, all whose derivative is the same thing. So we'll do just a couple more to finish off the video. 2x cubed, it's antiderivative. We would have x to the 4th. We would have 2 over 4 then, or you could reduce that to 1/2. So the 1/2 is coming from it would be 2 over 4. And then we'll have x to the 8th. So we'll have minus 5 over 8. We have a constant, so its antiderivative would be 10x. And then don't forget your plus c on the end. In number 2 here, we have a constant, so its antiderivative is 4x. Always be careful with the negative exponents. When negative 3's exponent goes up 1, it'll be negative 2. So that means we need a negative 2 in the denominator out front. Well, that's negative 3 over negative 2, which will be a positive 3/2, and then plus c. Now this one here, we probably want to rewrite it to make it easier to work with. We can write this as 3x to the negative 2 plus 2x to the 1/2. Now that's easier to take the antiderivative. We'll have x to the negative 1 now, because our exponent goes up 1. 3 divided by negative 1 gives us negative 3 out front. We'll have x to the 3/2. And then to figure what goes out front, let's take it off to the side here. We'll have 2 divided by 3/2. Well, that's 2 divided by 3/2, which is 2 times 2 over 3. That will give us 4 over 3. So we'll really have plus 4 over 3 out front. And then finish off on the end with your plus c. So your exponent goes up 1. Out front, you have your original coefficient over that new exponent for any of our polynomials. And in general, our antiderivative is just going basically backwards from our derivative back to the original. And since we don't know what constants were there, we have to put the plus c on the end to represent those constants. That's it for this video. We'll see you next class period.